morning. Today me and my friend gonna discuss about the mathematical modeling of thermal expansion piston rod case study. So we are from group 11. So I'm gonna introduce one by one our group member. First of all, Waki. Second, Daniel. Third, Ariel. And lastly, me, Zikri. Alright, so let's go. So the problem statement here, as you can see, the overview. Number 1, we are analyzing an internal combustion engine where a piston rod undergoes repeated thermal expansion. So the second one is the rod heats up and expands during every operating cycle. The conflict: if the rod extends beyond the maximum safe limit, which is M, the engine will fail. Right, so the second one, we must predict when this failure will occur using two different mathematical models. So group 11 parameters. So the first one is initial rod length N equals to 98.5 mm. So the second one is constant increase, which is D, 0.75 mm. So the third one, maximum safe rod length M, which is 111.5. And the last one is growth ratio, which is R, 1.0075 mm. So we are using the Pbl table to make our discussion more easier, which is F stand for fact, I stand for ideas, L stand for learning issues, and A stand for action. So the first fact is piston rod undergoes repeated heating and cooling cycles. So the second fact is thermal expansion causes an apa benda ni kan? So the second fact is thermal expansion causes an increase in piston rod length. So the third fact is initial length of the piston rod is known or assumed. So the fourth one is expansion occurs over a number of operating cycles. And the last one is a maximum safe length of the piston is specified. So we go into the next one, which is ideas. So the first idea is arithmetic sequence. The second idea is geometric sequence. The third idea is mathematical modeling. The fourth idea is sequence formulas. And the last idea is comparison with safety limit. Right, so the next one is learning issues. So the first one is rate of expansion per cycle. The second one is mathematical model for expansion. The third one is formula for piston rod length after n cycle. The fourth one is cycle number at which rod become unsafe. And the last one is condition when length exceeds safe limit. And the last of the Pbl is action. Identify whether expansion is constant or proportional. Select appropriate sequence model. Define variables and parameters. Apply arithmetic and geometric sequence formulas. And the last one is compare calculated length with safety limit. Alright, that's it.
So next, we do the solution for part A, arithmetic model. So part A, we start the part A, arithmetic sequence. Number 1 is formula. We using Tn formula. Tn equals to A1 plus n minus 1 times by D. So next we using the sum of the first n terms formula with Sn formula equals to n over 2 times by 2 times by an plus n minus 1 times d. So next we do the calculation. Number 1 is we do the calculation for extension at cycle 15. So we using this formula Tn. We change the n into 15, so it will be T15 equals to 98.5 plus 15 minus 1 times by 0.75. So the answer will be 109 mm. So next, we calculate the total extension after 15 cycles. So we using Sn formula. So we change the n like just now. So S15 equals to 15 over 2 multiplied by 2 multiply by 98.5 plus 15 minus 1 multiplied by 0.75. The answer will be 1556.25 mm. Next, we do the average extension per cycle up to 15. So the average will be we will using S15. So the answer we will use it for the average extension per cycle. So average equal to 1556.25 divided by 15. So the answer will be 103.75 mm. So next, the first cycle n when Tn greater than equal to m. So the first one we using 98.5 plus n minus 1 times by 0.75 greater than equal to 111.5. So we so 98.5 we transfer to the right side, so it will be n minus 1 times by 0.75 greater than equals to 111.5 minus 98.5. So so it will be n minus 1 times by 0.75 greater than 13. So n minus 1 greater than 13 over 0.75. The 0.75 will be transferred to the right side. It will be 13 over 0.75. So next, n greater than 17.33. The 1 will be transferred to the right side, so it will be plus 1. So n greater than 18.33. So next we do the calculation and table for 20 cycles. For the first one, we using Tn formula. Tn equals to A1 plus n minus 1 multiplied by D. So the first one, calculation. So we use 20 cycles. So we calculate 20 times to get the 20 items. So the first one is we using T1, and then 1 we replace to the n. So it will repeatable until T20. So the answer for Tn up to 20 cycle is 98.5, 99.25, 100, 100.75, 101.5, 102.25, 103, 103.75, 104.5, 105.25, 106, 106.75, 107.5, 108.25, 109, 109.75, 110.5, 111.25, 112, and the last one is 112.75. So next, the sum of the first n terms we using Sn formula. Sn equals to n over 2 multiplied by 2an plus n minus 1 multiplied by d. So next, the calculation will be the same. We replace the n to the S1 up to S20. So the answer will be 98.5, 197.75, 297.75, 398.5, 500, 602.25, 705.25, 809, 913.5, 1018.75, 1018.75, 1125, 24.75, 1231.5, 1339, 1447.25, 1556.25, 1666, 1776.5, 1887.75, 1999.75, and the last one is 2112.5. That's all for part A, arithmetic sequence. Done.
Okay, so for the next, I will do the solution for part B, geometric model. Okay, unlike an arithmetic sequence which adds a constant, the geometric sequence grows by multiplying a constant ratio at each step. To analyze this, we utilize two primary formulas. Okay, so the first formula is nth term Tn. Okay, this formula allows us to find the specific extension at any given cycle. Okay, so the second formula is Sn is equal to A times r power of n minus 1 divided by r minus 1. So this formula allows us to calculate the cumulative extension over time. In our model, our starting value A is 98.5 and our common ratio is 1.0075, representing a growth of 0.75% per cycle. Okay, so next we need to determine when the extension would exceed our threshold M of 111.5. By setting up an inequality and using logarithm to solve for n, we calculate that the failure point occurs at cycle 16.59. Practically speaking, this means the system reached its limit during the 18th cycle. The individual extension Tn starts at 98.5 and climbs steadily to 113.5252 by cycle 20. Okay, so next for the next formula, the cumulative sum Sn grows much more aggressively, starting at 98.5 and ending at over 2116.885.
Alright, for the comparison part, here we have a arithmetic model and geometric model. Arithmetic model predict failure at cycle 19 and geometric model predict failure at cycle 18. For the conclusion, the geometric model predict on earlier failure because the expansion accelerate over time, whereas the arithmetic model grows at the constant rate. For the discussion comparison, arithmetic predict failure at cycle 19 and geometric predict failure at cycle 18, which is more earlier. Finding the geometric model shows faster growth because the expansion compounds as the route gets longer. Safety amplification relying on the arithmetic model is dangerous as it overestimates the engine lifespan. Real-world factors align closer to the geometric model. For the discussion, engineering factor, operating temperature, higher temperature, faster expansion, material strength, weaker material, higher growth ratio, design tolerance, tired earlier failure. For the conclusion, lesson learned, mathematics modeling is critical for safety. It helps engineer predict failure points before they happen physically. Choosing the correct model can be the difference between safe operation and catastrophic engine failure. Thanks for watching.